So we'll get going. So welcome to this Thursday night physics. Today we're looking at the Waves 1 topic in OCR A-level physics. So this one really looks at a lot of the same content that is looked at in GCSE physics, but it just takes it to the next level and makes it that little bit more complicated. It's still very manageable though, and we'll see as we go through that actually a lot of these, they take a little bit of thinking about, but they're relatively straightforward. Right, so if we make a start, here is question 1. We're starting with some multiple choice questions, and these can be really good easy marks where you know that, well, you've got a pretty good chance of getting it right. You've got a minimum of a 25% chance, and it's about you narrowing that gap down and making sure you get it to 100%. Some of the questions, however, if you overthink them, will end up taking you a lot longer. And so with multiple choice questions, if you ever get stuck on one, I would highly recommend moving on and then coming back to them at the end. The reason for that is the questions later on, you might find one that actually you really do understand it and you can get those marks. And if you come to those with only a few minutes left or a few seconds left, if you're finding it hard to get through the paper, you're unlikely to get those marks in a few seconds. If you haven't got a multiple choice question the first time round, well, you're maybe missing out on a maximum of 1 mark, and that's 1 mark that you've got a 25% chance at least of getting, even if you just tick a random box at the end. But tonight we're not ticking random boxes, we're going through them carefully, and we will get to the answers. So, the diagram below shows the displacement time graph of a particle as a progressive wave travels through a medium. Which point A, B, C or D has a phase difference of 180 degrees with reference to point X? Well, the phase difference is saying, okay, if I was to start a wave out of sync, where would it end up? You can look at these with something called a phasor, which is the idea of if I had a pointer which was going around in a circle, where would it be at each point on the graph? So we've got 180 degrees in this, so we need something that's going to be 180 degrees out of phase with X. So I like to split my wave into portions so I can sort of get an idea. So if I make my own dots, one there, there, and there, sort of that is the total wave. So if I split that into quarters, I've got my 90 degrees of a wave. So that's 90 degrees, 180, and then 270 and 360. So we know that between there and there is going to be 180 degrees. So we're looking for a point. So X is just before this one. So we're looking for a point just before the next one. So that is C. Okay, so for me, I like to simplify these to make sure I've got the idea of it. So I do a nice simple set of points and then I can do just before, just after. So there is question 1. Question 2 is one of the types of questions that can cause some confusion because they are, which of the following statements are true? So these are a bit more complicated because you've got to read each of them to check what's going on. So a ray of monochromatic light is incident at a boundary between medium 1 and medium 2. The ray is both refracted and reflected at the boundary. So which of the following statements are true? So the way I like to do these is I'll go through each statement and either put a tick, that means I am confident that it's true, a cross, that means I'm confident it's not true, or a squiggle if I am not sure one way or the other. Because then it might be that in the options I've managed to narrow it down and we'll see what happens. So the refracted light and instant light have the same wavelength. Well, if something has been refracted, that means it's changed speed, but its frequency has to remain the same. So V is equal to F lambda. If its frequency has remained the same, but the speed has changed, that means the wavelength has to change. So the refracted light and instant light have the same wavelength. That cannot be true. The speed of light in medium 2 is greater than the speed of light in medium 1. Well, we'll come back to that in a minute. And the angle theta is the critical angle. Well, if the angle theta was the critical angle, well, that means that we were going to be meeting total internal reflection, and so there would not be a refracted ray because the refracted ray would be going along the boundary. So we know that is not true. The speed of light in medium 2 is greater than the speed of light in medium 1. Well, we can tell that this is true because the beam of light is bending away from the normal. So that one is correct. So that means that only 2 is correct. So the answer is D. But if you didn't know whether that was correct, you could work out potentially what it was, because all of them say that at least one thing is true. So if you knew that wasn't true and you knew that wasn't true, but you weren't sure about this one, you'd still be able to answer that question. So on to question 3. The diagram below shows the displacement time graph of an air particle as a sound wave passes. We have displacement in centimeters and time in milliseconds. So what the speed of sound is 340 meters per second. What is the wavelength of the sound wave? So our basic equation for this is going to always be V is equal to F lambda. Speed of the wave is equal to the frequency times the wavelength. Now we're not working out frequency. We're being given the time period because we've got time along here. So we can say that V is equal to 1 over T lambda. Or we can then just say that lambda is going to be equal to Vt. So we know 340 times, we can work out what our time period is going to be. So from peak to peak or trough to trough, so one peak to a second peak, it is 2. What is it? It is 2 milliseconds times 10 to the minus 3. Oh, can't see this. So that is then going to be equal to 0.68 meters. We can see here what would happen if we hadn't spotted that the units were different, that it was milliseconds. We would have selected D. We can also see what would happen if we hadn't recognized we need to do 1 over T and instead had divided by the time period, we'd have done B and C. So this is a really good example of how multiple choice questions can try and trip you up, because they've got to include distractors in the answers. So they've got to be very legitimate answers if you make a clear mistake or a simple mistake. So the answer to that one is A. Okay. Which of the following statements is true about electromagnetic radiation? So again, it's a which is true, so we can go through and try and narrow down the field. So radio waves are in the highest energy range of the electromagnetic spectrum. No. Gamma rays have the highest energy. They're at the lowest end. Visible light has a range of wavelengths in the order of 450 to 700. Ooh, I'm not sure about that one. Ultraviolet waves cannot be plane polarized. Well, all transverse waves can be plane polarized. It's not that one. Gamma rays have the lowest frequency. That's not true because they have the highest frequency. And I think all 3 of these statements are quite easy to see that they're wrong. You could be forgiven for having forgotten that visible light had a wavelength in the order of 450 nanometers to 700 nanometers. That one is the correct one, B. But even if you hadn't, by going through and actually saying which of these are false is sometimes easier than saying which is true. So question 4, answer is B. Powering through the multiple choice questions. Right. So the graph shows variation of displacement with time for a progressive wave. Which of the following statements can be deduced from the graph? Well, we could either work out the frequency of the wave is 5 Hz. Well, the graph represents a transverse wave motion. We don't know that. You could represent a longitudinal wave with this, because this is just a diagram showing displacement against time. The amplitude of the wave is 12 millimeters. No, the amplitude is from the line of zero displacement to a peak or a trough. So the amplitude is 6 millimeters. So it's not that. It's not that. The wavelength of the wave is 60 meters. Well, we can't actually tell that because we have time. So even just by doing this by a process of elimination, we can show that it is A, but we can also do the calculation and check for this one. So frequency is going to be 1 over the time period. The time period is 0.2, so frequency is equal to 1 divided by 0.2, which is 5 Hertz. So the answer is A. So this next question goes over the page. So I'll just read this and then we'll look at the next section. Hopefully you've got yours in front of you. So a ray of light passes through 3 media with refractive indices n1, n2 and n3. The speed of light in medium 1 is v1, in medium 2, v2, medium 3, v3. The angle between the ray and the normal in the medium 1 is theta 1, theta 2 in medium 2 and theta 3 in medium 3. Sounds very complicated. Fortunately, the diagram makes it much simpler. It's showing that we've got a ray of light going from medium 1 into medium 2 and into medium 3. And we're being asked which of the following statements are true. Well, for this one, I'm actually just going to work out what it would need to be. So Snell's law, you've got n1 sine theta 1 is going to be equal to n2 sine theta 2, which is going to be equal to n3 sine theta 3. Okay, so this is the generalized form, and it basically says if you're moving from one medium to another, if you know the refractive index and you know the angle of incidence, and you know the refractive index of the next material, well, and the angle of refraction, then you'll be able to work it out. So we're trying to relate, if we're seeing whether B is correct, we're trying to relate the speed in 3 to the speed in 1. So there is an equation that says that V1 over V3 is equal to sine theta 1 over sine theta 2, because remember that the refractive index is just a ratio of speeds. It's a ratio comparing the speed in a vacuum to the speed in the material. So if you do a little bit of maths, this is what it'll end up with. You're basically going from this to there. So if we rearrange this, by the way, spoiler, the answer is B, and you could go through and check each one. But the way you'd rearrange this is you could just say that V1 is equal to sine, that's meant to be a 3, theta 3 is equal to V3 sine theta 1. Oh, sorry, missing it there. And then when we rearrange this, we can say that V1 sine theta 3 divided by sine theta 1 is equal to V3, and so it's going to be B. Okay? So by that we can say that it is B. But you could do a similar thing going through each one and you could check whether they're correct or not. If this isn't one that you automatically spotted, I personally might have moved on from this one because it's a bit harder to check these individual things because they're not statements that you can immediately say whether one is true or not. Okay. So, out of the multiple choice and into the longer answer questions. So a guitarist manufacturer wants to investigate the quality of a sound produced from a new uniform polymer string. Figure shows the string, which is kept in tension between a clamp and a pulley. The frequency of the mechanical oscillator close to one end is varied, so the stationary wave is set up on the string. The frequency of the oscillator is 60 Hz. Use figure to calculate the speed of the transverse waves along the string. So what are we looking for? We're looking for the speed. We've been given a frequency, so we need to have an equation that's going to connect those two values. So V is equal to F lambda. So we basically know what we're looking for. We know that V is what we're looking for, The frequency is going to be 60 Hertz, and we need to find lambda, and we can find that from the diagram. So, what you can see here is 1.5 wavelengths. So we could say that, so we could try and measure it, or we can do this sort of mathematically. So a half wavelength is equal to the total distance, 0.54, divided by 3, because there are 3 half wavelengths, which is equal to 0.18 meters. Just stating this gets you 1 mark from your calculations. You can then show that the wavelength is going to be just 2 times that. So lambda is equal to 0.36 meters. And then it's just as simple as plugging that into the equation. So V is equal to 60, the frequency, multiplied by 0.36, which is in meters. So V is going to be equal to 21.6 meters per second. Is this how we should leave our answer? Well, no, actually, because this is 3 significant figures, and all our other units, so 60, 0.54, have been given to 2 significant figures. So technically, we should then round this to be 2 significant figures. So we can say, if we go back up here, that's approximately equal to 22 meters per second. So then we should write our answer in here, 22. I'm writing in Sharpie, which is why there isn't enough space, but that should have been enough space to go through all that working. So where do you get the marks for this? Well, you get a mark for identifying that, you get a mark for identifying that, and finally a mark for that. Or if you get the final answer correct, you'd get all 3 marks. Okay, here we have one of those questions that in theory should be 3 free marks. Because these are things that really should have been drummed into you from GCSE, so just remember them and pick them up. So define the terms wavelength, frequency, and time period using the used to describe wave motion. So lambda is the minimum distance between neighbouring, adjacent, identical points on a wave. That is the fully technical one, but they're going to allow anything like from peak to peak or from trough to trough, any statement which is basically saying from 2 same points on a wave. The frequency, this is the number of complete oscillations or vibrations at a point per unit time. You are allowed to say per second, but technically the definition is per unit time. So it's the number of oscillations per unit time. The time period is the time for one complete oscillation, or the time for one complete oscillation at a point on a wave. You are not allowed to just state it in terms of, say, 1 over frequency, because then you're using a definition of something else to define it. You need to try and get it back to its base idea. Right. Starting from the definition of speed v, derive the wave equation which relates frequency, wavelength, and velocity. Explain your reasoning clearly. Okay. So really, what we're needing to do is we need to go from speed is equal to distance divided by time, and we need to end up at v is equal to f lambda. So the speed is going to be a distance, travelled by travelled within the time period. So where do we have distance? Well, wavelength is in distance. So speed is equal to the distance, which is the wavelength, divided by the time, which is the time period. You would need to state this in a few more words, but I just don't have the space. You could then say that because time period is equal to 1 over f, well then v is equal to wavelength divided by 1 over frequency, which is going to be equal to frequency times lambda. The precise definition of the way they say they need to do it is speed is equal to the distance of one wavelength travelled per time period, where the period equals 1 divided by the frequency. So v is equal to lambda divided by 1 over f, which is equal to v equals f lambda. They don't want a derivation in terms of the units, but if you just talked your way through it and stated how they were a distance and a time, then that is what got you the marks. Okay. A student views the display of a laptop screen through a polarizing filter. The intensity of the light changes when the filter is rotated. What property of light is demonstrated in this experiment? Well, the wavelength shouldn't affect this. You can polarize or change the intensity of things other than electromagnetic waves, so it doesn't have to be traveling at the speed of light. You can polarize transverse waves, so it could be that. You can't transverse longitudinal waves, therefore it must be a transverse wave. This is really saying, do you recognize what types of waves can be polarized? And it's transverse waves that can be polarized. The reason for this is that longitudinal waves are only vibrating in one orientation anyway. So you can't change that. You can't decrease the number of orientations. So to polarize something, it has to be a transverse wave. Okay. This next question is also about polarization. So, in an experiment using microwaves, a metal grill G consisting of a series of long metal rods is placed between a transmitter T and detector D. The grill is slowly rotated through 180 degrees about the line joining T and D. The detecting signal at D varies from 0 to maximum and back into 0. Explain why the detected signal behaves in this way. Well, the first thing that you need to state is that microwaves, which you could say were from T, are polarized by the grill, or you could say that they are transverse, so can be polarized. Either of those things is going to be able to give you a mark. So at 0 degrees or 180 degrees, the grill is going to, oh, you can't see that. So at 0 degrees or 180 degrees, the grill is going to polarize all of it. It's going to block all of it. Whereas at 90 degrees, it's going to allow all the microwaves to pass. Okay? Yeah. So some common mistakes with this is that candidates will often not say that they are polarized, because how do we know that these microwaves are polarized? Well, it's saying that it varies from 0 to maximum. If they weren't polarized, even when the vast majority of it was being blocked by the grill, some of it would pass through, and so you would never get that 0 reading. You might still get a maxima and a minima, but you wouldn't get a 0. So if it was unpolarized microwaves, or partially polarized, you would get a maxima and a minima, but because it is fully polarized, the microwaves, that's why you're going to get the 0 reading. Right. Okay. Does anyone have any questions at this point? And here you see just how long the delay is. Okay, if you do have questions, pop them in the chat and I'll come back to them. the delay is actually quite long on this stream, so your questions might be coming through a little bit late. Okay, so here we have an image from an experiment that's making use of a ripple tank. So we've got a barrier, the waves are progressing in this direction. So a straight ruler repeatedly hits the surface of the water, waves on the surface of the water travel in the direction shown, the waves are incident at a solid barrier. Closely examine the image, state 2 wave phenomena or properties that can be observed in this image. You may annotate figure 19.1 to see this. Okay, well, what do we see? Well, to begin with, we see that there are waves that are travelling in this direction and then bouncing back off. Okay, so we're seeing reflection because you can see quite clearly here there are 2 arrows in there. So if we were to trace one of them, we could see that there is waves going there and bouncing off, and if we put the normal in, then we'd see that I was equal to R, with the instant being there. So reflection is one of them. And we can see some other things. So we can see here, it's quite faint on here, but we have waves that are coming up to this point, but there are still waves over here. So how are there waves there? Well, the waves that are reaching here are diffracting, so diffraction can be seen. Finally, we can see these different patterns here. So you can see this cross-cutting effect in here. This is interference. Or the superposition of waves. Because it says you may annotate, you don't have to. All you had to do was say 2 things that were correct. You didn't have to justify them. So this is one of the ones where actually if you guessed and had a good idea of what might be there, you could still get the marks because you just need to say 2 key terms. If it says state 2 wave phenomena, don't risk it by writing 3, as I did here. These are the only 3 that would be correct. Don't risk it by writing 3 because you're more likely to lose marks by getting one of them being incorrect than you can't gain any extra marks. And if you wrote anything wrong, then you would spoil your answer. And unless you'd managed to give a really good demonstration of where one of them were, you wouldn't even get 1 mark for this. So try not to over-answer questions because you're just giving yourself opportunities to lose marks. If they ask for 2 things, give them 2 things. If they're being more vague with it, so if it was just 2 marks and they said state the wave phenomenon, well then do state all the ones you can see because you don't know if those marks are being awarded 1 if you get 1 mark and 2 marks if you get all 3 kind of thing. Okay, so figure 5 shows the variation with distance of the displacement of 2 progressive waves P and Q. State the amplitude of P. So to find amplitude, I don't actually have a ruler here. Okay, imagine I had a ruler. We're needing to use the graph to do this, so we need to go to a peak or to a trough. So I'm just going to go to a peak because it's there. So I know I need to go from there to there, and I would go across. I'm doing this very scrappily, but in an exam I would have a ruler and I'd do that. And we could do, from that, we could see that it was 0.45 meters. State the wavelength of wave P. So we need to go from peak to peak or trough to trough. We can only see 1 peak, so let's go trough to trough. So there to there. And then you would read them off, again, using a ruler rather than just freehand. And then you could say that that was going to be 4.0 meters. Okay. So quite a nice straightforward one, just reading a graph. Perfect. It does, however, then get a little bit trickier. And what's going to be particularly tricky is that I need 2 sheets for this. So determine the phase difference in radians between wave P and wave Q. Okay. So we need to see the difference in phase between these two. So a good way to do this is going to be to think about when does one peak land versus the other one. So one peak is landing there and the other there. And we can measure the difference in the wavelength. Because their wavelength should be the same, the amount that the same point on a wave is off is going to be a fraction of that wavelength. So we knew that the total wavelength was 4 and the difference between those two was 0.5. So we could say that 0.5 divided by 4, or 1/8, is going to be sort of the fractional difference in phase. But we need to identify it in radians. So we can say that 0.5 over 4 times by 2 pi, because remember that 2 pi is a complete circle, which is going to be equal to pi over 4 radians. Or you could put that in decimal and round it to have 0.79 radians. Okay. Determine the ratio of the intensity of wave P and the intensity of wave Q. Now the reason why they're doing a ratio here is because you're not needing to memorize the equation for this. What you should have learnt is that intensity is proportional to the amplitude squared. So we need to find the amplitude and square it for wave P and divide that by the amplitude of wave Q when squared. So amplitude of wave P is 0.45 and we want to square that. And then we want to divide that by 0.15 squared. And then we calculate that. So 0.45 squared, 0.15 squared. And so the ratio is going to be 9. So the ratio of 9. Whenever you see something asking about determining the ratio, that's probably because you don't have the complete information to be able to work out the actual amplitude, the intensity of one of them. So it might be that you don't need to know the whole equation, or it might be that you have missing or incomplete information about it, but you can still work out the ratio between two things. Okay, moving on. And almost to the end. In fact, I think we're on the last question. Yes. Or last question. So, a progressive wave has a wavelength lambda, frequency f, and time period t. Show that the speed v is given by that. We've already done this question. But really, you just need to say that v is equal to the distance. We've done this again, but I'll say it again. The distance divided by the time. So v is equal to lambda, that's the distance of one complete wavelength, divided by t, the time period. F equals 1 over t. So v is equal to f lambda. Again, same as before. If you want to see a more complete one, have a little look back. Right, now the interesting one, because this one is worth a lot of marks. This one is worth 6 marks, so it is a levelled answer. Now, levelled answers can be a little bit tricky because you have to hit certain things to be able to access those higher marks. You can't just have the right indicative points. You have to have a coherence of thought going through the whole thing. So the speed v of surface water waves in shallow water of depth d is given by the equation v equals the square root of gd, where g is the acceleration of free fall. The speed v is about 1 meter per second for a depth of about 10 centimeters. You are provided with a rectangular plastic tray, supply of water and other equipment available in the laboratory. Describe how an experiment can be conducted in the laboratory to test the validity of the equation above and how the data can be analysed to determine a value of G. So it's asking you a couple of things. You're having to describe an experiment and you're having to test the validity of the equations. You're having to say what you would need to measure to be able to test this. But the key thing not to forget on this is there is an and. There are two parts to this question. So even if you gave the most perfect response for describing an experiment, you're still going to be locked into just getting 1 or 2 marks because level 1 is there. How the data can be analysed to determine a value for G. Right, so if we're trying to find a value for G, that suggests that we can measure 2 and we need to calculate the third. So firstly, let's have a think about the description of the experiment. So whenever you're thinking about an experiment, you need to think, what am I measuring? That's the first question. So I'm not going to write out the answer. It's not going to fit because of Sharpie. So I'm going to think about the questions that I ask myself as we're going through it. So what am I measuring? I need to measure the speed and I need to measure the depth. I then need to think, how am I going to measure these things? Well, if I've got wave speed, well, I'm not going to be able to measure that directly. So I'm probably going to use an equation where the speed is equal to the distance divided by the time. So actually, I'm going to be measuring the time and I'm going to be keeping a consistent distance, which I'll also measure. So I'm needing to measure the distance a wave is travelling. I'm needing to measure the time it takes to travel there, and I'm going to need to measure the depth. So how am I going to do each of these things? Well, the distance, well, I can have a consistent distance, so it's a rectangular plastic tray, so I'm going to measure that using a ruler. How am I going to measure the time? Well, a stopwatch. And how am I going to measure the depth? Well, I can use a ruler again. There are other things you could measure, but here are some sensible things. So I know roughly what needs to happen, but now I need to describe in a bit more detail what I need to do. So I would need to create a wave somehow and try and do that consistently. So it could be dropping the tray, doing a pulse, dropping a ball in the water. I could get a ripple tank. All of these things are possible. I then need to talk about how I would measure each of these things. I would also need to talk about how I would try and get my results to be better. Well, there's going to be some variation in the time. So maybe you could do the time it takes a pulse to travel there and back again. So doubling the time. Why would you want to do this? Well, there's going to be error that comes in due to your reaction time. So if your reaction time is a set amount of time or a similar variation, you can reduce the percentage uncertainty that's causing by increasing the time you're measuring. So by letting it go, say, there and back again, or getting a big tray or whatever, then that will help you to do that. Okay. You could also say you could repeat multiple times to find an average for V. So if you'd done that, you would get your indicative points, so the content required to get you any of the levels you need, as long as you also do this next part. Because again, if you just did this, you'd get a maximum of 2 marks. So let's have a think about what we'd need to do for the analysis. Well, analysis, generally what you should be thinking is, can I plot a graph? And spell, can I plot a graph? Because if you're doing practical work, actually trying to get values from gradients or intercepts is a better idea than just doing a single calculation, because it allows you to do another kind of averaging through it and remove anomalies by having a line of best fit in there. So we can look at this and think, okay, how can I get G to be either a gradient or an intercept? So this time it's got to be a gradient. So then you rearrange, so you have y equals mx plus c. So if we have v equals the square root of gd, well, we could say that v squared is equal to gd. So if we plotted, so y is equal to mx, if we plotted v squared against d, well then our gradient is going to be g. Okay? So being able to state, well, I would draw a graph plotting v squared against d, and I would make sure that I was varying depth and measuring the speed, well then saying that your gradient was going to be g would be fine. Okay, that brings us to the end of this paper. I'm going to wait around for another 5 minutes or so. If anyone has any questions to ask, then please pop them in the chat and I'll reply to them. But this will be where the recorded video is going to end. So if you found this helpful, please consider liking the live stream and the video, because it just sort of gives me a nice little morale boost. And if you think this is something you'd like to watch in the future, then consider subscribing to the channel so that you will be able to see when I'm going live, which should be every Thursday at around about 7. So hopefully you found this helpful. Good night.